Welcome, students. In this video, we are going to study the concept of continuity. We'll start with the definition of continuity of a function at a point. Then we'll take a look at definition of a continuity of a function at an open and closed intervals. Then we'll study several useful theorems and properties that are going to help us to answer whether specific functions are continuous or not. And finally, we'll end on intermediate value theorem. So let's start. A function f is said to be continuous at point C, provided the following conditions are satisfied. So we have three conditions here. First, function at that point should be defined. Second, two-sided limit should exist. And last property is these two should be equal to each other. So two-sided limit of f of x as x is approaching to that point C should be equal to the value of function at that point. Let's take a look at the following examples. So first example here, we see that two-sided limit here exists since one-sided limits exist and they are equal to each other. So second condition here is satisfied. However, first condition here is not satisfied since we can see that function at point C is not defined. So this function is not continuous at point C. However, we can easily fix that by plugging in a value in that missing point C. This discontinuity at point C is also called as removable discontinuity. Since two-sided limit here exists, however, even if it's not equal to the value of function at that point, since the value of function at that point is not defined, even though this function is not continuous at point C, we call this type of discontinuity as removable discontinuity. All right, next example here. We can see that second condition here fails. First condition here is satisfied since function is defined at point C. However, second condition here is not satisfied. We can see that one-sided limits, so left-sided limit as we approach point C from the left and right-sided limit as we approach point C from the right, they are not equal to each other, meaning that two-sided limit doesn't exist. Here, we cannot fix that problem by simply plugging in a single point here. And this type of discontinuity is called as jump discontinuity. All right, next example. First condition here is satisfied since the value of function at point C is defined. It's some value here. However, we see that even though we see that two-sided limit at point C doesn't exist, since function blows up here, one-sided limits are equal to plus infinity. And if you recall from our previous lecture, when a limit of f of x goes to infinity, we say that this limit doesn't exist. All right, so this type of discontinuity is known as infinite discontinuity. So basically, second condition here fails. All right, next example. here, first condition is satisfied since we have the value function at point C is defined. Second condition is also satisfied. We see that one-sided limits exist and they are equal each other, meaning that two-sided limit exists. However, the third condition here is not satisfied since two-sided limit is not equal to the value function at that point. Since second condition here is satisfied and two-sided limit exists, this case here is also a case of removable discontinuity. Because we can fix that by simply plugging in this point here, moving it from there and plugging it back at this missing value here. Now let's take a look at the following example and let's determine whether this function here is continuous or not. First, let's consider the case when x is not equal to 2. Then h of x can be presented as x minus 2, x plus 2 over x minus 2. If x is not equal to 2, then we cancel out these two terms here, and we'll end up with a line. And this line is continuous everywhere, with the possible exception maybe at point x is equal to 2. Now let's check whether h of x is continuous at point x is equal to 2. We need to show that a two-sided limit exists and it is equal to the value of function at that point. So value of function at that point, at point 2, is equal to 4. Now let's check whether our two-sided limit is equal to 4. Limit as x is approaching to 2 of x squared minus 4 over x minus 2 is equal to limit. If we expand this as a product and cancel out with the term in denominator, we'll end up with limit as x is approaching to 2 of x plus 2, which is equal to 4. So we have shown that all three conditions for continuity of a function at the point are satisfied, meaning that our function h of x is continuous at point x is equal to 2. And at the left side here, we have shown that it is continuous everywhere else, meaning that our function is continuous everywhere. All right, next. First, before looking at continuity of function on a closed interval, let's define continuity of function on an open interval. So a function is said to be continuous on an open interval if it is continuous at every point C, that is inside of open interval. So f is continuous on open interval from A to B if it is continuous at every C inside of this interval here. All right, now we can extend that definition here to a closed interval. A function f is said to be continuous on closed interval from A to B if the following three conditions are satisfied. First, it should be continuous on open interval. Second, when we are approaching left endpoint of our interval A from the right, let's show that. So when we are approaching our left endpoint from the right side, that that two-sided limit should, that one-sided limit, right-hand-sided limit should exist and should be equal to the value function at left endpoint. And third condition is that when we are approaching our right endpoint from the left, our function should be continuous from the left. By that, we mean that left-sided limit as we approach right endpoint should exist and should be equal to the value of function at right endpoint. Okay. All right, now let's take a look at a couple of examples of continuity of a function in a closed interval. Let's say we have the following function, and let's say we are interested in continuity of that function on interval from a to b, on closed interval from a to b. And let's assume that our function has a removable discontinuity. Assume that there is no point here. Removable discontinuity at the left endpoint. Now, one-sided limit, when we are approaching, let's assume that this value here is given as k. So one-sided limit as we are approaching our left endpoint from the right side. Let's assume this is graph for f of x is equal to k. However, as a function, in that case, the value of function at this point at left endpoint is not defined. F of a is not defined. Is not defined, meaning that our function is not continuous when we are approaching left endpoint from the right. So basically, this expression here, this statement here means that right-sided limit should be equal to, should exist and be equal to the value of function at that point, at that right endpoint. Okay, and similarly, f should be continuous from the left at right endpoint. This statement here is satisfied, this condition is satisfied, since limit as we are approaching to right endpoint from the left side exists. Let's assume that this is some value m. It exists and it is equal to the value of function at that right endpoint. So our function is continuous from the left at point B. All right, and in this case, our function, coming back to this example, our function is then not continuous on closed interval. But it is continuous on open interval from A to B, since we don't need this, these two conditions. And it is continuous on every point of this interval here. Okay, now if we take a look at this plot, this function is continuous on closed interval from A to B. Another example, let's say that we have function like that, and let's assume that right endpoint is removed and placed on top somewhere here. So we are fine with the left endpoint. Well, first of all, we can see that function is continuous on open interval from A to B. How it is continuous on, it is continuous from right on the left endpoint, but it is not continuous from left at right endpoint. even though the value of function here is defined, it's not equal to the right-sided limit when we approach this point B. Okay, another example is, let's say, this function here is not continuous on closed interval, and it is also not continuous on open intervals from A to B, since we can see that the value function at some point inside of this open interval is not defined, meaning that function will fail to be continuous at that point. All right. Now, here is a theorem that shows us several nice properties for two functions. So we have functions f and g. Both of these are continuous at point C. Then their sum is also going to be continuous at C. Their difference is also going to be continuous at C. Their product will be continuous at that point C. And their ratio is also going to be continuous at point C as long as G at point C is not equal to 0. If G at point C is equal to 0, then this ratio here has a discontinuity at C. Okay. And we'll be using these properties on our next video when we'll be solving a practice sheet on section 1.5. Next theorem is polynomials are continuous everywhere. A rational function can be presented as a ratio of two polynomials, meaning that we can apply the following last property here. And as long as denominator is not 0, a rational function is going to be continuous. All right. Let's take a look at the following rational function. So this is x minus 3, x plus 3, divided by one root is 2, second root is 3. All right, this function is continuous everywhere with the exception of 2 points, x is equal to 2 and x is equal to 3. At these 2 points, our function will be discontinuous, and on top of that, we can see that at x is equal to 3, we have removable discontinuity. And at x is equal to 2, this rational function has infinite discontinuity since it blows up. Next theorem is 1.5.5. If limit as x is approaching to C of g of x exists and is equal to peak L, and if function f is continuous at point L, then a limit of f of g of x is equal to, as x is approaching to C, is equal to the value of f at point L. Which means that limit as x is approaching to C, f of g of x is equal to f of limit as x is approaching to C of g of x. And since here we have two-sided limit, obviously it can be replaced by one-sided limits, and also that will be true for limits at infinity. Right, now let's use that nice property to show that we can move limit across the absolute value sign. So first we know that x bar function f of x, which is defined as absolute value of x, is continuous everywhere. If you take a look at the plot of absolute value of x, then we can see that it is continuous everywhere. Now, secondly, let's assume that a limit as x is approaching to c of g of x exists and is equal to some big L. And then, since absolute value function is continuous and that limit here exists, then we can apply this theorem 1.5.5 and move that limit inside of absolute value sign. Okay, next theorem. If function g is continuous at point c and function f is continuous at g of c, then their composition f of g is continuous at c. And if function g is continuous everywhere and function f is also continuous everywhere, then their composition will also be continuous everywhere. Let's prove part A. So g is continuous at point c, meaning that limit as x is approaching to point c of g of x exists and is equal to some big L. We also know that f is continuous at g of c. Or at L. Then according to this theorem here, we know that two-sided limit of their composition exists and is equal to f of L. Meaning that their composition is continuous at point C. So basically what we need to show is that composition is continuous at point C. To do so, we need to show that the value of their composition at point C is equal to this two-sided limit of their composition at point C. Let's show that this can be brought to this form here. Since here we can apply theorem 1.5.5, then we can move limit inside of function f. I mean, what I meant is, let's write this down as in the following form. We'll have f limit of g of x as x is approaching to point C. And now this is exactly since g of x is continuous at point C, this is exactly g of c. So we'll have f of g of c, which is simply the value of composition of these two at point C, which we needed to show. All right, now using this theorem, we can show that absolute value of a continuous function is continuous. Oh, by the way, guys, regarding the part B, we can use part A to prove part B by simply setting up an arbitrary value to point C on interval from -infinity to +infinity. Okay, so then we can prove that this here will hold true for any value C on interval from -infinity to +infinity, which basically means that their composition is continuous everywhere. All right, now absolute value of a continuous function is continuous. So first of all, let's assume that we have function g of x that is a continuous function. Let's assume that is continuous. Let's check it on at some point. Let's say C is continuous at point C. Secondly, we know that absolute value function is also continuous. We know that it is continuous everywhere, meaning that it will be continuous at G of C. Now, using the following two properties, we can apply theorem 1.5.6. Then their composition is continuous at point C, meaning that which we needed to show. So absolute value of a continuous function, g of x is a continuous function, is continuous. All right, finally, we'll end on intermediate value theorem. If function f is continuous on closed interval from a to b, and k is any number between f of a and f of b inclusively, then there is at least one number x in interval from a to b, such that the value of function f of x is equal to k. This can be represented nicely in the following graph. Let's assume that we have continuous function on interval from a to b. On closed interval from a to b. So here is the value of f of a. Here we have value f of b. Now, the theorem here can be represented geometrically by selecting any value k on interval from f of a to f of b. And now if we are going to draw a horizontal line y is equal to k, then we can see that that line is going to intersect our function at least at one point. So basically that theorem, this is geometrical representation of that theorem here. Intermediate value theorem can be used nicely to approximate roots of equations. So if f is continuous on closed interval from a to b, and if f of a and f of b are non-zero and have opposite signs, then there is at least one solution of the equation f of x is equal to 0 in the closed interval from a to b. This theorem here is a special case of intermediate value theorem. Let's show that. Let's assume that our function is continuous on closed interval from a to b, and let's select f of a and f of b such that their signs are opposite. Let f of a be negative. And f of b be positive. Then 0 lies in closed interval from f of a to f of b. I mean open interval from f of a to f of b. 0 is in open interval since it cannot be equal to f of a or f of b, since we said that f of a and f of b are non-zero. So by this reason, this interval here is open. So when 0 is in that open interval, meaning that according to mean value theorem, horizontal line at y is equal to 0 is going to intersect our function f of x on closed interval from a to be at least once. So this interval is not closed anymore since we said that f of a and f of b are non-zero. All right, guys, now that will conclude our video on section 1.5. Thanks for watching.